Hello, this is going to be a little tutorial on not only the answers to the practice test that you did the other day, but also a little bit about what to expect when you come in for your examination. First of all, you're going to come in and you'll see what they're referring to in this bullet point. It's where it says for each question, you're going to mark it on the answer sheet provided. That sheet is going to be at your desk, and you're going to find out what desk you belong to when you get in there. They're assigned. You can't move where you are. You just sit at the one that has your sheet. And there will be on the projector the seating chart as well, so you can find it easily. Remember to come in quietly and in an orderly manner to make sure that you're being as respectful as possible. The answer sheet is not like a regular Scantron. You're not filling in bubbles. Instead, you're going to be marking X's in either A, B, C, or D for each of the questions as you go down. Now, when you are marking your answer on these, you need to be using a pencil, and you cannot use a pen on this. You have to use a pen on paper 2 and 3, but you cannot use a pen on this. So make sure you've got a pencil for paper 1, a dark pen, so preferably black, so that when it gets scanned in, you actually get the correct answers that you're supposed to get, because the grader can actually read your stuff. But on here, again, you must use a pencil. I want to remind you that there's a periodic table provided. There's not one up in the classroom that you're going to be in. You're not going to be able to bring one in with you. The only thing that you can bring in with you is that pencil for paper 1 and the pens for paper 2. The calculators will be provided for you. You shouldn't be bringing that in. If you accidentally have your cell phone on you, or if you've got a smartwatch or a Fitbit, all of those things have to be turned in before you enter the room. We'll go through some directions when you get in there, and then you'll be allowed to take paper 1. And paper 1 is, as you can see up here, just 45 minutes. There's no reading time with this. When you get to paper 2 and paper 3, you'll get 5 minutes to read through the instructions and the possible different sections that you could take, so you can figure out which one you want to do. But you do not get this on paper 1, because paper 1 clearly is just answering every single one of the multiple choice questions. So let's take a look at some of these problems that you had here. This first one, we're looking for the relative molecular mass of water, and all of these numbers are the same, so you don't even have to calculate anything. You don't even need to look at the periodic table. All this one is asking you to do is to remember what the units are for molecular mass. And we have used them over and over and over again when we've been doing any of our calculations dealing with balanced equations and stoichiometry, so hopefully you remember that it is 18.02 for our moles or grams per mole. Ooh, there we go, grams per mole being our answer for molecular mass. That's the correct unit for it. Number 2 is not too tough, but we can't use, because there's no fractions here, we can't use a fraction in front of the O2. We know that sometimes we can get away with that shortcut, but that won't work here because we don't have anything in halves. So when you balance this one out, it's going to be a 4 in front of the NH3, a 3 in front of the O2, a 2 in front of the N2, and a 6. Oops, my 2 got a little funny, and so did my 6. Gotta love when they try to format stuff for you. So that's a 2 and a 6. That it's asking for the total sum of it, so I would add all of those together. 4 plus 3 plus 2 plus 6 and 15 would be my answer. Now, this one was easy in comparison to some of the ones that you might get at different times. It's not even letting me erase it. There we go. Every once in a while it will give you one where the answer is with one of these being a 1, and people forget, since they don't have to write a 1 in front of something that's a 1, they forget to add it into the total. So just don't let that be you. Don't say, oh, it's just 4 plus 3 plus 2 if that was a 1, and then we'd have the wrong answer. So make sure if you just have 1 mole of it that you include that 1 mole in your final answer. This one, we're talking about two things here. We're talking about state changes, and we're also talking about energy changes. So an endothermic process, just in case you don't remember, is where we have energy required for reaction or process to happen. Oops. So that's what an endothermic process is. So I need to think about all of these different ones here. We'll try to use this funny little pen again. So we know that we go from a solid to a liquid to a gas. Solid to liquid to gas, and those processes are listed out here for a couple of them. So our Roman numeral 1 is melting. Melting is when I go from a solid to a liquid. We're used to that in Minnesota in the spring. So that would be my melting. I'll do a Roman numeral kind of 1 there. And then we also have condensing. That's going from a gas to a liquid. Gas to a liquid is condensing, so that's my Roman numeral 2. And then I also have the process of subliming. Subliming is when I go from a solid directly to a gas. We see that in Minnesota in the winter when we have ice built up, and then all of a sudden it starts decreasing in size, but it's not because it's gotten warm enough for it to melt. So we've got 1, Roman numeral 2, and then Roman numeral 3 up here for my different changes. Well, going from, in this diagram, left to right is where I'm requiring energy. Oop. So energy, it's not going to let me do that one nicely. So energy is needed as I go from left to right. I need energy to go from a solid to a liquid or a solid to a gas. When I'm going from a gas to a liquid, I'm going to actually release some energy that was built up in the system. So if I need energy to happen, it means I need it for processes 1 and 3 only, because those are the only two going in that direction. So B is my correct answer. Number 4. This one is all about remembering a little bit of stoichiometry and not actually worrying about calculations, which is nice. So in general with this one, I'm going to have actual divided by the theoretical, oops, and then multiplied by 100 to get it into percentage form. So that's my general equation for this one. And I know what my actual is. It says that 2.40 grams are produced. So I know that that one right there, 2.40 grams, that is my actual. But I need to calculate my theoretical. My theoretical is not given to me. So let's set up my fraction. I'm going to put the 2.40 on top. I'm also going to put that times 100 on top right away. So that's going to be my numerator to start out this process. And let's get a line here representing my fraction. And then let's do the denominator. And the denominator is going to include more fractions. So it's difficult for me to do with this program, but I'll use parentheses to help us out. So we're starting out with our given, and our given is that 5.00 grams of the calcium carbonate. I also can't easily make that subscripted, but I know I would make it subscripted if I had that capability. So that's going to be multiplied by whatever I can do to get rid of grams of calcium carbonate to get to moles of it, which I'm going to use that molar mass. So it tells me that my molar mass of calcium carbonate is 100 grams per mole. That goes back to that first question on this paper. So if I have 100 grams per mole, I'm going to have 1 mole of CaCO3. 3 divided by 100 grams of the calcium carbonate. And then I'm going to multiply that next by a 1-to-1 molar ratio, because in my balanced equation, for every 1 mole of calcium carbonate I have 1 mole of calcium oxide formed. So 1 mole of calcium oxide goes on the top because that's what I want to get to, and 1 mole of calcium carbonate goes on the bottom. And let's make this smaller here so we can actually see it, see where we're at with this. There we go. So we're making progress. Next up, I want to get rid of my moles of calcium oxide to get to grams, because it's the actual grams over the theoretical grams. So I'm going to have my 56 grams of calcium oxide on the top for every 1 mole of calcium oxide. And now I can start clearing this up a little bit, because I can see here that none of these have units, and none of this has this crazy stuff on the bottom. So what we are going to do first is double check that all my units cancel out. We've got grams of calcium carbonate on the top, grams of calcium carbonate on the bottom, so that canceled out. Mole of calcium carbonate on the top, mole of calcium carbonate on the bottom, so that cancels out. Mole of calcium oxide on the top, mole of calcium oxide on the bottom. I'm left with grams of calcium oxide, which is what I wanted. So let's get rid of some of these things that don't matter. The ones don't matter, and the units are not going to matter for me. So we got rid of a lot of stuff there. That whole fraction gets to go away because it was just 1/1. Get rid of the unit there. Get rid of the unit there. Oop, I lost a parentheses. That will help us out, so put that back in. And then the unit there. Now this still isn't very pretty looking because I've got a fraction that has a fraction in the denominator. So that means I have to remember what happens when I have a fraction in the denominator. Now, let's say I had 1/1/2, or 1 divided by 0.5. Hopefully you remember that that just inverts my denominator's fraction into 2. 1 divided by 1/2, or 1 divided by 0.5 would be 2. So that's the same thing that's going to happen here. My 1/100 gets flipped. I have to invert it to get rid of the 100 on the bottom. So that means I'm going to have another 100 on the top that I'm multiplying by. So let's clear this up. That goes away. Oops. And grab the wrong one there. Move this over. Now I can check if one of these is the correct answer. Sure enough, B is 2.40 times 100 times 100 times 56 times 5. B is the correct answer. Okay, number 5 is trying to help us remember what happens when energy is either absorbed or released. Anytime I have arrows going down, that means energy is being released into the surroundings. So energy is released when I go down, but to go up in energy, energy has to come in, or from one lower energy level to a higher energy level, energy is needed. So I know that it's either going to be B, because it's going in the upward direction, or D, because that is also going in the upward direction. So then I just have to reason through what is happening. Okay. There we go. So we know it's going to be B or D. The shortest wavelength is the one that has the shortest distance that it's traveling. So this one between energy level 2 and energy level 3 would require the shortest wavelength to occur. So D is the correct answer. Then we get to our nuclear symbol. It's called our nuclear symbol, and it's the AZX. And so we've got AZX, and we've got a Q here too, something dealing with the charge. So we just need to remember what all of those different things mean. in A, the top number, which in this instance is 238, is equal to the number of protons plus the number of neutrons. And again, if I could superscript easy here, I would do that for you because we'd be able to see it a little bit better. This is plus means that protons are positively charged, and the 0 means that neutrons are 0 charge. And then we've got our Z value, which in this example is 92, and that's our atomic number, which is the number of protons. Then we have a Q value of 2 positive, which is our charge, and that's going to be either because it's lost electrons or gained electrons. In this instance, it has lost 2 electrons from what it originally was. Originally, the atomic number, the number of protons, is equal to the number of electrons when it is an atom, so it's when it's neutral. This one's not neutral, this one has a charge. So whatever I know about my protons is going to be 2 less for my electrons. So let's take a look here. First of all, I know that A cannot be my answer because it does not match my number or my atomic number. So 146 is not the number of protons that I have. It has to be either B, C, or D. And then I look at my number of neutrons. Well, I see right away that 238 could not possibly be my number of neutrons because my mass is 238, and mass includes the neutrons plus the protons. So it could not possibly be D. That leads me to B or C. The only difference between these two is whether it is lost 2 electrons or gained 2 electrons. We said that if it's a positive charge, it must have lost those 2 negatives, those 2 electrons, so it cannot be C. B is our correct answer. Number 7, this is remembering the different parts of the periodic table. Let's get some different sections here, if I can get one that is not filled. Nope. We'll draw some out. So, these will come important for the next question too. So we've got our S, our D, and then our P, try that one again. And then finally our F is at the bottom. So we need to look then at the periodic table at the different locations, S, P, D, F. The one that's in the F block is B. The cerium is located down here in our F block. If you weren't sure, beryllium you'll find in the first 2 columns, so that's the S. If you're looking for germanium, it's going to be over in the P block, and then the rhenium is going to be in the D block in the center. Number 8 is talking specifically about group 1. That's this first column in the S block. That's what it's talking about. And we're looking at going down. So we're looking from going from hydrogen all the way to the bottom of that column, and we're trying to figure out which property would increase as we're going down. Well, let's look at melting point first. We know that we're going to be referring to the Z. Let's try writing it this way instead. The ZEFF, the effective nuclear charge, is what that stands for. That's the pull that the electron had, or that the nucleus has on the electrons that are surrounding it. That's the effective nuclear charge. Well, we know with each energy level that we add, so as we're going down we're adding energy levels, each energy level that I add, the further out the electrons naturally are from the nucleus. And that means that the inner electrons are going to shield the effect of the nuclear charge from the outer electrons. So my ZEFF, my effective nuclear charge, decreases as I go further and further down the periodic table because I'm going further and further out from my nucleus. So melting point would actually decrease as I go down the periodic table because it is going to be less held by the electrons or by the nucleus, and so it's much easier to break apart those forces that are holding the uh, nuclei of the element together. So it's much easier to melt, which means it's decreasing the melting point. So it's not A. B is the first ionization energy. First, as a reminder, the first ionization energy means the energy required to remove an electron from the outer shell. So it's actually much easier as I go down the periodic table to remove an electron from the outermost shell because the ZEFF, the effective nuclear charge, is less. So it takes less energy because there's less pull from the nucleus. So it would actually be decreasing the first ionization energy. It's much easier for lower elements on the first column to have an electron removed from it. To C, we've got the atomic radius. That's going to, as I go down in energy levels, get further and further from the nucleus, just because each energy level is further from the nucleus. So that is actually going to increase as I go down the periodic table. So that should be my answer. But let's look at the last one just to verify and to remind ourselves what electronegativity is. And electronegativity is the pull on shared electrons. So will they, if they have the same electronegativity, how much are they pulling on all those shared electrons? Well, again, the further I go down the periodic table, the weaker the effective nuclear charge is. So those outer electrons, or that outer electron, since it's got one valence electron, is not going to be held as tightly, and therefore if it was to form a bond where it was sharing electrons, it would not be holding on to those electrons well. That's why those are going to form ionic compounds. So we can cross off D. So C sure was our answer. Number 9, we are looking at ionic bonding here, key word here being ions. So let's take a look. Each of these have electrostatic attraction as part of their definition. The bottom one, electrostatic attraction between nuclei, they're not going to have electrostatic attraction because they're all going to be positively charged. So this one just is illogical to start with. Then we've got electrostatic attraction between nuclei, of the nuclei towards shared electrons in a bond. This, hopefully when you see shared electrons, reminds you that shared electrons are referring to covalent bonding. With any luck, you're remembering that. Covalent bonding is where electrons are shared in the bond, and so the electrons are being held together with that electrostatic charge of the nuclei. So that is not our answer. That is not an ionic bond. That's covalent. B is the electrostatic attraction between positive ions and electrons. This is that sea of electrons that we see with metallic bonding. The electrons are floating around all of these positive cations of the nuclei of a bunch of metals that are not holding on to their outer electrons very tightly. So that would not be our answer either. Our final one, electrostatic attraction between oppositely charged ions. There's my keyword, ion, ionic bond. Oppositely charged ions are going to be attracted by electrostatic forces in an ionic bond. A is our answer. Number 10, which has bonds with the greatest covalent character. So that means we're looking for something with similar electronegativity values, or in other words, near each other on the periodic table. We can rule out tin right away. A bunch of tin together would be similar to this one right here, the electrostatic positive ions and their electrons. It's just metallic bonding. So that's not being covalently bonded at all. Then we've got strontium with chlorine. Those are very different parts of the periodic table. We've got one from the S group and one from the non-metal group, the halogen group more specifically. So they're very far from each other on the periodic table. Their electronegativity values would be very different, and therefore it would be ionic bonding, not covalent bonding. Then we're down to two that are more similarly related than the previous two. Silicon is a nonmetal, chlorine is a nonmetal. They're close to one another on the periodic table, so that's probably our answer, but let's look at the next one. We've got tin, which is a semi-metal, and chlorine, which is a nonmetal. Those are slightly further apart than the silicon and the chlorine, so they're going to be a little less similar, so less likely of being covalent. So we're going to go B as the correct answer. They're closer together, their electronegativity values are closer to one another. Number 11, which of these is the least polar? Well, we could look at the molecules overall, and that's not bad practice for us. So if we were to draw out CO2, this one will be easy for me to type. We've got oxygen double bonded to a carbon, double bonded to another oxygen. I know that this is a linear molecule. Again, I don't need to do this to figure out this answer, but it's going to help us remember how these different things work. Linear molecule with a degree angle of 180. It's got a central carbon atom that has two electron clouds, and both of those electron clouds are bonds, therefore we get linear. But it's really talking about the difference between the oxygen and the carbon atom, because we know this molecule overall would be nonpolar because it's the equal amount of unsharing on either side of it. But we're looking just at that oxygen to the carbon. Those are greatly differing electronegativities, so that will be quite polar. So that's not our answer. We've got an amide down here that has, let's find a way to draw this one not too horribly. This isn't one of our normal shapes, and I can't do, again, the subscript quickly, so NH2, imagine that the 3 and the 2 are subscripted. Oops. Here we go. So it's talking about the NH bond. That would be a little bit further on the periodic table and should actually have more of a pull. Remember that if we had a bunch of these together, there would be hydrogen bonding involved in between molecules. That's the key word for our intermolecular forces, is between molecules. So if I had a bunch of this, CH3NH2 methylamine, if I had a bunch around together and I was trying to figure out what held them together, it's the force between the intermolecular forces, and we would have hydrogen bonding because hydrogen bonding occurs when there's a hydrogen bonded to either fluorine, oxygen, or nitrogen, because there's a great electronegativity difference between the nitrogen and the hydrogen, which would mean it's quite polar. So that's definitely not our answer either. Then we've got CCl4. That would be tetrahedral, as well as the CH4, also tetrahedral. They do have 4 electron clouds, all 4 of those electron clouds being bonds, tetrahedral. Don't get fooled and think that tetrahedral is a 90-degree angle just because that's the way you draw it in a 2-dimensional form. Remember that molecular shapes are in 3 dimensions, and so it is not 90 degrees. It's closer to 109 for the angle between those molecules. So that means we're looking at the electronegativity differences between carbon, hydrogen, and carbon, chlorine. The carbon, hydrogen electronegativity values are actually closer to one another, so that would be my least polar of the bonds between them. Again, this linear molecule and these 2 tetrahedral molecules would both be nonpolar overall. they'd have no dipole moment. But this one's just specifically looking at the bond that's involved in these first two things. And I think that's where we're going to stop for this video.